All right, here we are once more for the very last time to talk about the wonderful world of statistics. So let's make it count for this last time. So what do we have on the agenda for today? Well, I started the A lecture with introducing logistic regression, and we finished with lots of information on how to interpret effects in logistic regression analysis. So we talked about interpreting effects as effects on log odds or on odds. There is one more thing we need to talk about, a third way of interpreting effects in a logistic regression model, and that is interpreting effects as predicted probabilities. So that's what I'm going to continue on first for this lecture. And then we'll have a recap on the binary logit model, so see what we now know about this binary logit model. So once we have done that, we can go a little bit more into the technicalities behind the logit model, sort of behind logistic regression analysis. So we'll start out with talking just very briefly, to the extent it is relevant, about the binomial distribution and what role that plays in logistic regression. And once we know that, it will be easier to understand how logistic regression models are estimated, how we can say something about the goodness of fit of our logistic regression models, and how we can compare different nested logistic regression models in terms of goodness of fit. And then we'll close off with discussing the assumptions that we make with a logistic regression model, and of course what happens if those assumptions aren't true, if they are violated. And we'll also discuss some technical potential issues that you might run into if you do a logistic regression analysis. So let's dive in. So we already saw that we can interpret effects in logistic regression model as linear effects on the predicted log odds, so linear and additive effects on the predicted log odds, but that's not very intuitive because log odds, that's a double mathematical transformation from a probability into an odds and then taking the natural logarithm of that. So mathematically that makes sense, but it's quite hard to understand what that really means because we are on this weird double mathematical transformation. So we already saw that we can simplify things a little bit by getting rid of the natural logarithm for our dependent variable, putting that on the right hand side of our regression model, and then we get effects on the predicted odds ratios, and we do that by exponentiating the coefficients. And then we get a multiplicative model for the predicted odds. So by how many times do the odds increase if our x variable goes up by 1 unit on its scale, which is already a bit more intuitive because at least we got rid of the natural logarithm in the interpretation, but it's still quite hard to interpret because odds are not the most intuitive way of thinking about how likely it is that something happens, because it's that ratio of, well, how likely is it that something happens relative to how unlikely it is that something happens. So of course it would be even more intuitive if we could just interpret our effects as effects on the predicted probabilities themselves, because that's what we started out with when we started talking about categorical data analysis. If you have a categorical dependent variable, what you are really interested in is probably, well, the probability of some event happening and how that probability changes if your independent variables take different values. So in other words, what we really want to know about might be, well, how do the predicted probabilities change if our x variables go up or down. So the cool thing is that actually we can use math to rearrange our logistic regression model, so this linear additive model for the log odds, in such a way that we actually get a model for just the predicted probability. So this is just, again, a mathematical transformation where the model is exactly the same. We're not substantively changing anything, we're just rearranging it in such a way that we're getting rid both of the natural logarithm as well as the odds, and just are left with just the value p on the left hand side of our regression model. And so that means that we put everything, all these transformations that have happened to our dependent variable are now going to happen to our independent variables, basically, and then we get this nice model for the predicted probability, meaning that if we can solve this model, we get just a predicted probability for our cases, which is great. And this is also probably the first model that you saw in the book that you have read. So again, it's just a different way of presenting the same model. And there are also different ways of writing this model. So this is the one that's being used by Field. There is a different one which you might also sometimes encounter, but again, it doesn't matter. They are all mathematically equivalent. So this one, how does it work? Well, 1 divided by 1 plus Euler's number to the negative power of, and well, negative power of what? What is the exponent then? Well, it's the entire regression model that we're estimating. So b0 plus b1 times x1 plus b2 times x2, and so on and so forth. So this is just a way of rearranging our model in such a way that now we have a model for predicted probabilities, which of course is awesome, because that means now we can say, well, okay, what is the effect of our independent variable on the predicted probability that whatever it is that we want to analyze happens. That's great. That's awesome. However, if you look at this formula, it looks quite unlike anything you have seen so far in this course, because if you look at what is on the right-hand side of the equal sign, it is actually a fraction. So it's 1 divided by 1 plus Euler's number to the negative power of our entire regression model multiplied by the values on the x variables, which has certain consequences, because this is not a linear and additive model. It is inherently a nonlinear model, because that's what we want it to be, because remember, we want the effects on our predicted probabilities to take the S-curved shape. Yeah. So looking at this from a mathematical standpoint, well, there is two things that stand out. One is we cannot actually now compute changes in the predicted probability without knowing the values for all our x variables. Otherwise, the formula is just not solvable in that way. So we can't, with this model, we can't just say, well, this is how the predicted probability changes if x goes up, without looking at the other variables in our model. So that's not like in the linear regression model. Remember, in the linear regression model, we could just always reinterpret our unstandardized regression coefficients as, well, this is by how much the predicted value in our dependent variable goes up if the independent variable goes up by 1 unit on its scale, controlling for the effects of the other variables in the model. So we could also always just look at those isolated coefficients for the independent variables to interpret the effects. And because it's just a linear model with a straight line, the effect then was always the same. It didn't really matter what the values on the other x variables was. In the logit model, if we want to have effects on predicted probabilities, we can't do that. We can't calculate changes in predicted probabilities without also knowing the values of not just the variable that we're interested in, so the x variable that we want to say something about its effect. We also need to know then the values of all the other x variables in our model to compute these changes in predicted probabilities. And yeah, it is a nonlinear model. By definition, it makes sure that the effect that we are estimating of our independent variable on our dependent variable takes this S-curve if it's a positive effect, or reverse S-curve if it's a negative effect type shape. That's what we want it to do after all. But that also means that if we talk about changes in predicted probability, now it matters, well, okay, from where to where are we going on the S-curve? So from where to where are we considering changes in the predicted probability? Because again, it's not a linear model. So it now matters where we are on the x-axis. It now matters what the value of our independent variable itself is, and what the range of the independent variable itself is, for which we want to consider the change in predicted probability. Yeah, if you're at the bottom of the S-curve, so if you're very close to the zero value on the dependent variable, then the increase in predicted probability with an increase in x is going to be fairly small. If you are close to predicted probabilities that are around 0.5, then x is going to have a very big effect on the change in predicted probabilities. And if the predicted probability goes very close to 1, again, the effect of x on the predicted probability is going to become really, really small again, because that's what the S-curve describes, right? This effect that's first small, then increasing, and then increasing ever further until we hit a predicted probability of 0.5, and then decreasing again until we hit a predicted probability of 1, right? So now all of a sudden it's also important to consider, well, for which range do we want to consider the effect of our independent variable on the predicted probability of our dependent variable. So that has a couple of consequences in how we are able to and how we need to illustrate the effects of our x variables as changes in predicted probabilities. So there's a couple of steps you need to go through if you want to do that. Well, first thing, of course, if you have estimated your logistic regression model, so then you get a linear additive model for the predicted log odds, well, first rewrite this model in such a way that you get a model for the predicted probability, right? So whatever your regression coefficients are that you estimated for these models, put the values of those into this formula for the predicted probability. So that's step one. Step two would be, well, think about, okay, I want to say something about the effect of one x variable on my dependent variable, on the predicted probability of the event happening. For what values on the other x variables do I want to show this predicted probability? Because again, the predicted changes in predicted probability are also depend on what are the values on x2, x3, x4, x5, all the other x variables in your model if you want to show what the effect is of x1. So you need to pick values for the other x's in your model. Which values you pick is a bit arbitrary, depends on how you want to illustrate your effect. So for instance, you could just pick the mean values if you're really not sure how to do that, or some other variables that might interest you. But you need to pick some values for your x variables. And you need also to consider, well, okay, over which range do I want to illustrate the effect of my independent variable on my dependent variable? So going from where to where on that x variable do I want to show how the predicted probability changes? And again, there it is in theory arbitrary which range you pick. It really depends on, well, what exactly is it that you want to show. So for instance, you could say, well, maybe I'm going to look at the effect from the lowest observed value on x to the highest observed value on x, or from one standard deviation below the mean value on x to one standard deviation above the mean value on x. Now, all of those are possible. It depends really on how do you want to show the effect, but you need to pick a range for your x variable so that you're able to show, well, okay, from here to here on the x variable, this is how the predicted probability on my y variable changes. And once you have done that, then what you can do is, well, then, okay, calculate the difference in predicted probability for the lowest and the highest value of your x variable. So for the lowest value that you picked on the range for x and the highest value that you picked on the range for x, which means that you have to calculate the predicted probability twice, once for the lowest value on the x variable and once for the highest value on the x variable, and then calculate the difference between those two predicted probability to see how much did the predicted probability increase if it's a positive effect or decrease if it's a negative effect, going from that lowest to highest value on your x variable. So that's how to do it in theory. Now let's take a more practical example so that it becomes a bit more clear, hopefully. So in the A lecture, I showed you that I estimated the effect of a couple of independent variables on voting in a national election using some old European social survey data. And one of the effects that I included, one of the X variables that I included was income. So I included income as an X variable. So let's say I want to illustrate this income effect. Maybe I want to test the hypothesis about the income effect, and I found an effect that it's statistically significant, and it's also in the direction that the hypothesis is predicting. So I want to actually show, okay, what does the effect actually look like? So remember what, you probably don't remember, but these were the regression coefficients that I found for my logit model for voting. So I included income, age, and a gender dummy variable in that model to explain differences in the log odds of voting. And the logit model that I found was a constant of minus 0.873 plus a coefficient for the dummy variable female of 0.099. Plus a regression coefficient of 0.025 for the age variable, plus a regression coefficient of 0.177 for the income variable. So we know that we can interpret those coefficients as this is by how much the predicted log odds of voting increase with a 1 unit increase in the independent variable holding the effect of the other variables constant or controlling for the other variables. But now let's do this for predicted probabilities. Well, first step is just rewrite the model that we now have a model for the predicted probability. So in other words, fill in the formula 1 divided by 1 plus Euler's number to the negative, and then just fill in the entire regression formula that we have estimated. So minus 0.873 plus 0.99 times the female dummy plus 0.025 times age plus 0.177 times income. Okay, so that's step 1. Step 2, now we need to consider, okay, if we want to show the effect of income on a predicted probability, we need to say something about, okay, at which values for the gender variable and the age variable do we want to show this effect of income on the predicted probability of voting. And again, it's more or less arbitrary which ones you do whatever, which values you pick, do whatever best fits with your research question. So in this case, I just thought, well, let's pick women and let's pick 30-year-old women. So I'm giving a value to the variable for gender, and I'm giving a value to the variable for age. Yeah, so in this case, 30-year-old women, meaning that the female dummy variable is going to take the value 1 and the age variable is going to take the value 0. So the second thing I need to consider is, okay, for which range of income do I want to show the change in predicted probability for differences in income? So in this case, I just figured, well, the income variable that we're using is household deciles. It runs from 1 to 10. So let's pick the lowest value and the highest value and pick that as the range over which we want to show the change in predicted probability. So, in other words, what I'm saying here is I want to show how the predicted probability of voting for 30-year-old women changes if we go from income 1 to income 10. So by how much does it increase? Okay, so that's step 3. Now step 4 is working this out. So in other words, using the formula to work out how does the predicted probability of voting change for a 30-year-old woman when we go from income 1 to income equals 10. Well, fill in the formula. So P equals 1 divided by 1 plus Euler's number to the negative power of the entire regression model. And now we can fill in the values for our X variables. So I picked women as the group for which I want to show this effect of income. So the female dummy variable gets the value 1, so we can fill that in the formula. I picked 30-year-old women, so the age variable takes the value 30, so I can fill that in the formula. And I need to first calculate the predicted probability for the lowest of the two income variable values that I picked, which is 1. So I can fill in the value 1 in the formula where we have the coefficient for the income variable. Right, so now I'm going to use this formula to calculate the predicted probability of voting for 30-year-old women that have the lowest decile of household income. And as you've seen by now, I can just calculate that probability because now I have numbers and only numbers in my model. So now I can actually work out what comes out of that. So let's do that step by step. And as always, stop, pause, and see if you can get the result for yourself with your calculator at hand. Yeah, that's going to help you understand what's happening, of course. Yeah, so the first things I do is, well, there is two coefficients in there that I would multiply by 1. So that's the female dummy coefficient and the coefficient for age, because those both get the value 1. So I can just multiply those by 1, which means that we get the same value. So now we have already simplified our model a little bit to minus 0.837 plus 0.099. So that's just 0.099, the coefficient for the female dummy multiplied by 1, plus 0.025 times 30 plus 1 times 0.177, the coefficient for income multiplied by 1, because we are looking at the predicted probability for income, the income decile 1, the first income decile. So that's already simplifying the formula quite a bit. We can of course also work out the 0.025 times 30 for the age effect. That works out to 0.075. Now we can of course just add up all these numbers. So minus 0.837 plus 0.099 plus 0.75 plus 0.177. That works out to 0.189. So now we have already further simplified the formula to P equals 1 divided by 1 plus Euler's number to the negative brackets 0.189. Well, negative brackets 0.189 is the same thing as saying minus 1 times 0.189, which works out to just taking the negative of that number. Yeah, remember, negative times positive equals negative. So in this case, we have minus 0.189. So now we have already simplified the formula to 1 divided by 1 plus Euler's number to the negative 0.189. So exponentiating that value gives us a result of 0.828. So now we know that the predicted probability is 1 divided by 1 plus 0.828, which works out to 1 divided by 1.828, because 1 plus 0.828 is 1.828. And that is just a simple fraction that we can solve that works out to 0.547. Great, now we have solved this entire model for a predicted probability. In this case, the predicted probability of voting for a 30-year-old woman in the first decile of household income, and that probability is 0.547. Great, so now we know the predicted probability of voting for 30-year-old women that are in the first decile of household income. Now we need to do it again, of course, because we also want to know, well, what is the predicted probability of voting for 30-year-old women in the 10th decile of household income. So again, just fill in the formula, fill in the values in the formula. Notice that everything here now stays the same as it was in the first step, or in the first instance that we solved this formula, except for the value that we fill in for income, because now we're going to do this for income equals 10. So we're going to multiply that coefficient for the income variable of 0.177 with the value 10. So again, do it step by step. First work out the coefficients that are multiplied by 1, because then it's just the value of the coefficient. So again, nothing changes for the gender variable, so we have a value of 0.099 for that one. For the age variable, also nothing changes. It's still 0.025 multiplied by 30, because we're considering 30-year-old women, so that still works out to 0.75. For the age effect, now we see, well, it's 0.177 times 10, so that's now different. That works out to 1.77. Okay, great. Now we can just add up all the numbers, so minus 0.837 plus 0.099 plus 0.75 plus 1.77 works out to 1.782. Again, we have now 1 divided by 1 plus Euler's number to the negative brackets 1.782, which is the same thing as minus 1 times 1.782, which works out to minus 1.782. Remember, negative times positive equals negative. Yeah, so in this case, we see that, that this works out to minus 1.782. So now we know what to do. We need to take Euler's number as the base number, and as the exponent, we're going to pick minus 1.782. Exponentiating gives us 0.168. Okay, so now we can say, what is the predicted probability? It's 1 divided by 1 plus 0.6168. So 1 plus 0.168 equals 1.168, of course. And 1 divided by 1.168 works out to a predicted probability of 0.856. Okay, great. Now we have the predicted probability of voting for 30-year-old women in the 10th decile of household income, and it is 0.856. Great. So the last step, how does the predicted probability of voting change for a 30-year-old woman when moving from income 1 to income 10? Well, let's calculate the difference in these two predicted probabilities. Yeah, so let's subtract the probability of voting for 30-year-old women from in the 10th decile of household income, and the first decile from the first decile household income from the 10th decile of household income. Yeah, so the 10th decile of household income, the 30-year-old women had a predicted probability of 0.856. In the first decile, they had a predicted probability of 0.547. So 0.856 minus 0.547 works out to 0.309. So now we know the difference in predicted probability, and we can now say, well, what is the effect of income on the predicted probability of voting for 30-year-old women? Well, for 30-year-old women, the predicted probability of voting increases by 0.309 when moving from income 1 to income 10. So when they go from the first income of household decile to the household income decile to the 10th decile of household income. So that's a pretty substantial increase in this case in predicted probability. Okay, so that's how to do that. As you see, it is quite labor intensive to calculate these predicted probabilities and changes in predicted probabilities. But it is necessary if you want to say something about the effects in terms of predicted probabilities. Of course, as always, SPSS can automatically calculate predicted probabilities for you. As a matter of fact, if you use the predict option like we did with the linear regression models when we save predicted values, this is what SPSS will do for you. It will calculate for each case the predicted probability based on the observed values on the X variables that you put in your model for those cases. But it's important that you understand what SPSS is actually doing then. And so this is what SPSS does for you when it calculates these predicted probabilities. I put an SPSS syntax example of using SPSS to calculate predicted probabilities on Brightspace. So you can work through that yourself if you want to see, well, okay, exactly what does it look like in SPSS and what does it tell us. Yeah, so that's for that basically. Now let's take a step in place and have a bit of a recap. What do we now know about this binary logit model, this logistic regression, this model that we use for logistic regression analysis? Well, we know that we can look at the model itself, which is then the natural logarithm of p divided by 1 minus p. So in other words, the log odds of the event happening equals b0 plus b1, x1 plus b2, x2, and so on and so forth. So we have a linear additive model for the predicted log odds. We know that we can rewrite this model to get in such a way that we get rid of the natural logarithm in front of the equal sign by putting it on the right hand side of our model, and then we would exponentiate the regression coefficients that we found, and then we get a multiplicative model on the predicted odds. In other words, we get a model that tells us what the effects are in terms of odds ratios. Yeah, so by how many times can we multiply the odds with a 1 unit increase on our X variables. And now we have seen that we can also rewrite the model in such a way that we get a model for the predicted probability, and then we get this nice nonlinear S-shaped effect on the predicted probability. Just takes a bit of time to actually work out the results for the predicted probabilities, because unlike the log odds or the odds ratio formulation of the model, we can't just look at the coefficients themselves and immediately have an interpretation. Now we first have to work through the formula to actually get to actually understand what that means for predicted probabilities. Okay, so these are 3 equivalent ways of interpreting the logistic regression model. And again, the underlying model is the same, so there is no substantive difference between these 3 different ways of writing the model. It's just which one of those you want to pick. It depends on, well, how do you want to illustrate your effects. So log odds is completely correct, but it's not very intuitive. Odds is a bit more intuitive. Predicted probabilities is even more intuitive, but yeah, each has some benefits and trade-offs, so to say. Yeah, so for predicted probabilities, it's a bit more labor intensive, and it depends on the values of the other X variables and the range of your X variables that you're considering. Yeah, so but these are 3 different options of interpreting these logistic regression models. Now let's look at some of the technicalities behind that. And one thing that we need to start out with is something that I already briefly touched on in the A lecture, but so far we didn't really need it. Now we need to consider it a little bit, the role of the binomial distribution in logistic regression analysis. So remember, when we have this model for our some event happens, then if we rewrite the model as a model for the predicted probability, then we get this S-curved effect if it's a positive effect, and this reverse S, it would be a reverse S-curve if it would be a negative effect. So that would be the effect of our independent variable on the predicted probability of our event happening. But of course, all we observe for individual cases is whether or not the event actually did happen for that case. Yeah, so we only observe zeros, the event did not happen, and ones, the event did happen. We can't actually observe for an individual case, yeah, this probability, because really for an individual case there is only one observation. So this probability itself is only something that we can say over the entire sample that we have. Yeah, so that is what the logistic regression model does, but notice that this has an implication, because our regression coefficients tell us how steep this S-curve is. So is it a very spread out S-curve, that means it's a pretty weak effect, or is it a very, very steep S-curve, that means it's a strong effect. But because we can't observe probabilities for individual cases, we can only for individual cases observe zeros and ones, we have a bit of an issue here, because that means that we can only find our regression coefficients that describe this S-curve if we make an assumption about the differences between what we predict and what we observe. Yeah, because all we can observe is zeros and ones. So in other words, our regression coefficients describe the shape of this S-curve. But we can only find values that describe this shape appropriately if we make some kind of assumptions. Okay, what is then the difference each time for each case between what we predict and what we observe? Because that's the only way we can pin down exactly what this S-curve is supposed to look like. Yeah, so we only have 0 and 1 observations. We somehow need to use those to come up with the correct S-curve. Well, if we just have zeros and 1, I mean, there is an infinite amount of possible S-curves that we could draw running through these observations, right? I mean, this is one possible S-curve, but we could have drawn a much steeper S-curve that runs something like this. Or a much flatter S-curve that runs something like this. The only way we can actually find a shape for this S-curve, so the right actually a value for our coefficients, is if we make an assumption about how the errors are distributed. So this is really different than in a linear regression model. In a linear regression model, we just minimize the sum of squared residuals and let them be whatever they are. In a logistic regression model, that doesn't work. We need to actually make an assumption about the distribution of our error term to be even able to find values for our coefficients. Now, in formal terms, this is referred to as a so-called identifying assumption. Identification is the idea that you set it up in such a way that, at least in theory, if you have data, you can find values for our for your regression coefficients in this case. And so in this case, we see that we can only do that if we actually make an assumption about the distribution of errors. So this is a so-called identifying assumptions. Without this assumption, we can't even if we have data, we can't find values for our regression coefficients. Okay, so this is something that this blah blah about identifying assumption. That's something you are allowed to forget, but that's what is behind this. But there is something you should know. If we have the logistic regression model, what we do is we make one specific assumption about the distribution of error, and that is that this distribution of errors is the one that is implied by the binomial distribution. Yeah, again, what is the binomial distribution? Well, it's basically the distribution you get if you flip a coin. Yeah, what is a coin being heads or tails? And then you can observe, well, how many times do I get heads, for instance? And how many times do I not get heads? So in other words, how many times do I get tails? So the binomial distribution is basically the distribution that describes this coin flip. And if you think about that, well, if you're analyzing whether or not some event happens, that's kind of the same process, right? Something either happens or it doesn't happen. A coin either comes up heads or it doesn't come up heads. So it makes a lot of sense to consider the binomial distribution as the right distribution for our events if we are interested in these binary dichotomous events where either something happens or it doesn't happen. And the nice thing is, if you actually have binary data, meaning for each individual event you can observe whether or not the outcome happens, then this implied distribution of error can be described by a very simple formula, namely p times 1 minus p. So if we are assuming a binomial distribution of the errors and we have binary data, so we observe for individual cases whether or not they have a 0 or a 1, whether the event happened or it didn't even happen, then the assumed distribution of the error is just the probability times 1 minus the probability. So whatever our probability value is, the error is assumed to be that probability value times 1 minus that probability value. Which, if you work that out, what does that mean? That means that if you have probabilities that are very, very close to 0 or very, very close to 1, you get very, very, very small errors. And the closer you move to 1 or the closer you move to 0, the smaller your errors become. And the further you move towards 0.5 as a probability, the larger your errors become. So if you would fill in different values for the probability, like 0.1, 0.2, 0.3, 0.4, all the way up to 0.9 and 1, you would see that the corresponding errors, so the result of p times 1 minus p, is kind of like a curve. Where first, for low probability values, the error is very, very small. Then as we move towards 0.5 for the error becomes very large. And then if we go over 0.5, the error becomes smaller and smaller again, which is exactly what we have if we have this S-curve here, right? We have small error values here, and then the more we go to a predicted probability of 0.5, the larger the error becomes. And then from there on further, the closer we get to a predicted probability of 1, the smaller the error again becomes. I put up an Excel sheet, as always, on Brightspace, where I did this for you and made a nice little graph so you can actually see that this is in fact true, that we have a distribution of errors that is small for values close to 0 to 1, and in between gets larger and larger towards the value of 0.5. So that's great, because now we have a variance of errors, so a distribution of our error term, where we say, well, how much variation we have in our error actually depends on what the probability is that we are talking about. Yeah, so the variance of our error now depends on the value of p. In other words, where are we on the S-curve, which is an assumed heteroscedasticity, if you think about that, right? Because if the value of the error depends on where we are on the S-curve, that also means that the value of the error depends on, well, what is the value of our X variable, because those will change the predicted probability. So in other words, if we have a logistic regression model, we assume a binomial distribution of our error, which means that how large the error is actually now depends on the values of our X variable. Yeah, remember one of the problems that we would have if we would have estimated a linear regression model for this, for a binary outcome or something either happens or it doesn't happen, is that we assume with a linear model homoscedasticity, and that absolutely wouldn't be the case if we would estimate a linear model. In this, here we see for logistic regression model, we don't assume homoscedasticity. No, we actually assume that the variation of our error itself depends on the value of our X variable. So there is already a built-in heteroscedasticity. So that's exactly what we would want, because that's a more appropriate distribution, description of the distribution of errors in this case. But as you see, the errors is something that we cannot actually estimate. We have to make an assumption about them, because we can only observe zeros and ones. That means that if we want to find values for our regression coefficients, we have to actually assume what the distribution of errors is like, because we can't actually observe it independent from the probability itself. So that has a couple of consequences. For one, unlike in the linear model, we can't use OLS to estimate our regression model, because, as you see here, we haven't added an error term to our logistic regression model, not because we don't have an error, but because A, the error is assumed, and so not estimated from the data, but we simply assume what its value is, and B, it is not independent of the values of our X variable, so it doesn't make sense to just add an error term here of some value, because the value of the error itself depends on the values of all the X variables in our model. So in other words, OLS was the idea that we have an error term, and if we're talking about the sample, then we're talking about the residual, and we're just going to minimize the sum of squares of those residuals. But for a logistic regression model, there is no single constant value of the residual if we just look at the distribution of errors. So we cannot minimize that value because it is an assumed value that we can't directly observe. That means we can't use OLS to estimate logistic regression models. Fortunately, there are other ways of estimating our models, and the one that is generally used to estimate a logistic regression model is the so-called maximum likelihood estimation procedure, often shortened to MLE. So MLE, that stands for maximum likelihood estimation. So a very, very rough idea on how that works. Maximum likelihood, the word likelihood is in there. So what does likelihood mean? Likelihood is basically a statistical measure, so it's a number that shows you how likely values are for the parameter estimates given the observed data. So in other words, you can think of this as a number, that the larger the number is, the more likely something is. And what are we talking about when we talk about likely? Well, think about our B0 and B1 and B2 and B3 coefficients. They could take different values, right? We could give them the value 0.1 or 1.2 or 88 or 7.6. So all of those, we have potential values that we could assign to all our regression coefficients. And so what does the likelihood tell us? It tells us how likely these different values would be given the data that we actually have observed, that we use to estimate the regression model. So in other words, you could think of the likelihood as indicating, well, how likely are the values for the parameter estimates given what we actually have observed. And of course, then what is the best model? Well, the best model is that model that maximizes the likelihood. So that is the model where the values that you assign to your b-values are the most likely values they could take given the data that you have actually observed. So that's the logic behind maximum likelihood estimation. It's the idea that we can calculate a likelihood for different hypothetical values of our regression coefficients, and then some regression coefficients will be more likely than others given the data that we observed. So let's find the values for these regression coefficients that are the most likely given the data that we have observed. And that's what it is, what maximum likelihood estimation basically does. Now, for the types of models that we're talking about here, there is a difference between maximum likelihood estimation and OLS estimation, because with OLS, as you might remember from the second week, there is a formula. We can put in the values that we observe for the variables that we are interested in that formula, and then a result will come out. Yeah, so we saw that we could even do that manually, and it's just one formula, and that we can just solve. And that is also what SPSS is doing for us. If we're using an OLS to estimate a linear regression model, there is a formula for that, and it just uses the observed data to solve that formula, and then the results come running out for our regression coefficients and our standard errors. Now, with these types of models that we're looking at here, the maximum likelihood estimation, there is not a single formula that can just be solved in one go. So that's just how here we have the formula, we put in the numbers that we observe, and then we have a result. In mathematical terms, we would say it is not a closed form solution, but you are absolutely allowed to totally forget about that. But the consequence of that is that we actually need to go through what is called an iterative process, meaning we're going to repeatedly try to solve this formula, and then for each time that we solve the formula, we get a value for our coefficients, and then look at, well, okay, what is the likelihood for these coefficients, and then systematically change the values of the coefficient until we see that the estimates converge to the maximum likelihood. In other words, that no further change in the values of our regression coefficients would be able to further increase the likelihood, so that we find those values for the coefficients that have maximized the likelihood. So this is an iterative process, so which really means that what SPSS is doing if you run a logistic regression model is it is basically providing tentative solutions to these formulas multiple times over and over again. So each time SPSS does that is called an iteration. Yeah, that's where the iterative process terminology comes from. And it does that multiple times using some smart ways of doing that until it sees, hey, the coefficients don't further changes to the coefficients no longer improve the likelihood, so I have found the maximum likelihood, and that's then the result that comes out that is presented to you by SPSS. So if you ever wonder about why it is the case that if you do an OLS model, then usually you hit run in your syntax comments, and then within virtually no time you get results. Whereas with a logistic regression model, you will sometimes notice that it takes a while until you get results. And the more complicated your model is, and the more data you have, the longer it will take. And it's sometimes, if you have very complicated models, it can really take quite a lot of time for SPSS to be able to find the maximum likelihood estimates. So that's the reason behind that. So it's really a bit more computationally intensive. It demands a little bit more work from your computer to actually find find the right coefficients for your logistic regression model. So that's the estimation procedure. And again, the reason why we can't use RLS is because we don't have a single independent residual that we can just observe. And no, we actually have to make an assumption about what that residual looks like. So that's maximum likelihood estimation. So this is also going to have consequences for how we talk about the goodness of fit of our models and how to compare the goodness of fit between different models. So if we are doing a maximum likelihood estimation, like a logistic model, then what we can look at for the goodness of fit would be the so-called deviance statistic and so-called pseudo R-square values. So let's take a look at those. So what is deviance? Deviance is formally defined as -2 times the log of the likelihood. So we just saw what the likelihood was. The likelihood is some statistic that tells us something about, well, how likely are our estimates, our parameter estimates given the data that we have observed. So that is some number. Now, what is the deviance then? Well, it's just a double mathematical transformation of that number. So it's first taking the natural logarithm of that number and then multiplying that by -2. And then this is referred to as the deviance statistic. Yeah, so you could say the likelihood, the higher the higher the likelihood is, the better your model fits. Well, if you take a negative transformation of that, so the deviance, then that indicates, well, how bad our model is, right? So -2 times the log of the likelihood. So this is sometimes shortened to -2LL because it's very, very common to work with that. And one of the main reasons it is common to transform the likelihood into the -2 times log likelihood, so the deviance, is because this deviance we can actually use to test null hypothesis about the difference in goodness of fit between different nested models. So if we want to test the null hypothesis that there is no difference between two different nested models in terms of goodness of fit, so how well they fit the data, then we can actually test that null hypothesis with this deviance measure, because the difference in deviance, so the difference in -2 times log likelihood between two nested models, if the null hypothesis is true, that follows a chi-squared distribution where the degrees of freedom of that chi-squared distribution, so exactly what chi-squared distribution we're looking at, is identical to the number of constraints we are putting on the model to get from the more complicated model to the simpler model. Yeah, so this is sometimes referred to as the deviance test and sometimes also referred to as the likelihood ratio test, shortened to LR test. So the idea is that we can look at, well, okay, what is the deviance of the full model and what is the deviance of the constraint model? Remember, if we have nested models, that means that we have a more complicated model and a more simple model, and we can get from the complicated model to the simple model by taking stuff out of the complicated model, and taking stuff out is the same thing as constraining that stuff to taking the value 0. Yeah, remember this when we talked about F-tests to compare the goodness of fit of nested models. So yeah, we can do this for nested models and then look at, well, how many constraints did we impose on our full model? So how many things did we take out? How many things did we force to take to value 0? And that is then the number of constraints that we are putting on that simpler model. So what do we do then? Well, we estimate both models. We estimate the constraint model and we estimate the full model. And for both of these models, well, we get the likelihood, and we can transform that likelihood into -2 times the log of the likelihood, so into the deviance. And then the deviance, that will be our chi-square test statistic. The degrees of freedom is, well, the difference so the number of constraints you put on your more complicated model to get to the more simple model. And if you're talking just about simple logistic regression models, then that is basically, well, what is the difference in the number of X variables you put in your full model and in your constraint model? So how many additional X variables did you include in your more complicated model compared to your simpler model? So the difference between those two numbers, that's going to be your degrees of freedom. And that can be used like you would otherwise use the F test for linear regression models. So it's exactly the same type of logic that we have here. So we can use this to compare the goodness of fit of any two set of nested models. And for instance, you could do that for multi-parameter tests, as we have seen for the linear model, where we use the F test for that. So for instance, if you have a curve linear effect that you want to test, remember then we need to do a multi-parameter test for both of the coefficients that indicate the curvature relationship. Or if you want to test multiple dummy variables at the same time because they are about the same underlying theoretical variable. Like for instance, we had the situation where we had multiple dummy variables for religious denomination. So if you want to test the null hypothesis that all of those coefficients are 0 in the population at the same time, then we can do a multi-parameter test. Now we can see that we can also use this deviance test to do that if we have logistic regression models. We can also do this for testing single coefficients, where we could also do that in the linear model, but in the linear model it was really not useful to use an F test for testing just a single regression coefficient, because the result of the F test then was exactly identical to the result of the T test. So you would get exactly the same p-value whether you looked at the individual at the t-test for the individual regression coefficient, or you would estimate two nested models where the only difference would be that one additional regression coefficient, and then look at the F-change test statistic. Both of those would give you exactly the same p-value. For logistic regression models, this is not true. So remember, for the logistic regression model, we use the Wald test. So the coefficient divided by the standard error squared to test individual regression coefficients, which is great, but can be a bit unreliable, especially if you have a relatively small sample size and or if your coefficients are actually very, very, very large. So if you have large coefficients and or a small sample size, then the Wald test can be a bit unreliable. And then using the deviance test is actually a bit more reliable. So in that case, you will actually see that you will get slightly different p-values with using the deviance test for an individual regression coefficient compared to looking just at the Wald test. So it's always good, especially if you have hypotheses about certain effects of certain variables, that not only look at the p-value that comes out of the Wald test, but also use the deviance test where you include that one additional variable in your model, and then look at the p-value for the deviance test statistic, because that's going to be a bit more reliable than just you looking at the Wald test. So that's basically the analog of F-tests. Now we can also look at the analog of the R-square, because it's nice to be able to test nested models against each other, but maybe we also want to say just something about, well, how much variance are we explaining in our dependent variable in our model. The problem with that is explained variance in logistic regression model is not actually as straightforward as you might think it is. And that is, again, because, well, the error variance is an assumed variance. It's not something that we can just estimate from the data that we have. No, we actually have to make an assumption to even be able to estimate our model. And the variance of the error also depends on the probability. In other words, it depends on the values of our X variables. So that means that, explained variance is a bit of a difficult concept if you talk about logistic regression models, because there really isn't one variance in that sense. And it's also the variance that we're working with is actually an assumed rather than an estimated variance. Now, there are some ways to get around that and still have some kind of number that approximates what would be explained variance for our logistic regression model, so that you can interpret like the R-square value for a linear regression model. But the basic underlying idea of doing that is a bit problematic, because again, we don't have variance like we have in the linear regression model and the logistic regression model. So it is kind of weird at the end of the day to say something about explained variance. So this is the reason why these are sometimes usually referred to as pseudo R-square measures, because it's not really an R-square measure like the for explained variance like in the linear regression model, but it's trying to approximate what would be a good representation of the explained variance. So in that sense, it is useful. The problem that there is with this is that there are actually many different ways of doing that. So there's lots of different formulas that you can run to get a value for a pseudo R-square. And last time I checked, there were around, I think, more than 10. So then more than 10 different ways of calculating pseudo R-square measures. And of course, all of them are different and therefore will give you slightly different values. Because again, the issue is that, well, it is really at the conceptual level weird to talk about explained variance in a logistic model where we have an assumption about the amount of unexplained variance in our model. Yeah, but there are different ways of doing that, and there are situations in which it is useful. For instance, if you just want to have a quick, rough comparison of how well different models that your logistic regression models are in predicting the outcome variable, and you're using the same data, and you're just comparing different models for the same data, then it's a rough way of saying something about which models do a better job of explaining your dependent variables. So in that sense, it can be useful. So SPSS only provides two of all those different pseudo R-square values. It provides the Cox and Snell's R-square and the Nagelkerke's R-square, named after the people, the statisticians that came up with these different ways of calculating pseudo R-square value. It really doesn't matter which one you pick, again, because all of them are just pseudo R-square values. So they all have very specific benefits and drawbacks, which you really don't need to worry about. What is important, I think, is, well, at least if you're reporting on pseudo R-square values, be clear which one you are reporting on. So if you're using Nagelkerke's R-square, great, but then tell your reader that you are using Nagelkerke's R-square, and then stick to that one, and don't switch between them. So don't, for instance, do something where you say, well, for this model, the Nagelkerke R-square was super high, so I'm just going to report that. And then for another model, the Cox and Snell's R-square looked really good, so now I'm going to report that. So try to be consistent and try to be clear so that at least your reader knows which one you are using. And that there's actually, that we can actually at least to some extent compare the values that you get for the R-square. Yeah, so that's explained variance in a logistic regression model. Not straightforward, but we can say something about that. So let's look at the SPSS output that we would get if we run a logistic regression model and assess the goodness of fit of our model and compare the goodness of fit between different nested models. So one thing that SPSS will always give you for each model is the model summary, where we have, in this case, I just estimated one, I just have one model, so that's step one, indicates that I have one model here, and then I get different numbers with in different columns. So what do the numbers represent? Well, the labels are pretty clear in this case. -2 log likelihood is exactly that number. So this 1549.657 is -2 times log likelihood. In other words, that's the deviance of our model. The column that says Cox and Snell R-square reports exactly that, the Cox and Snell's R-square values. So in this case, you see that the pseudo R-square, the Cox and Snell pseudo R-square is 0.055. So I would say about 5.5% of explained variance. Next to that, we get the Nagelkerke R-square column, which surprisingly reports Nagelkerke's R-square value. And here you see that you get a slightly different pseudo R-square value because it's a slightly different formula to calculate that. In this case, we get an explained variance of 8.8%. So here you can see that these different pseudo R-square values really give you slightly different results. Yeah, so that's what they tell us in this case. Yeah, so Cox and Snell suggests basically that 5.5% of the variation of our dependent variable is explained. Nagelkerke's R-square tells us that 8.8% of the variation in our dependent variable in the sample is explained. Okay, so that's just the overall model fit, where it becomes really interesting if we compare nested models. So let's assume that I want to compare these two models. I have a model where I'm explaining differences in voting with differences in gender, age, and income, and I want to compare that to a more complicated model where I'm including on top of that a dummy variable for being Catholic, a dummy variable for being Protestant, and a dummy variable for other religious denomination, using the non-religious people as the reference category. So I might want to say, well, okay, what is the joint effect of Catholic plus Protestant plus other? In other words, I might want to do a multi-parameter test on the overall effect of religiosity. So notice that that implies that I would want to compare the model with Catholic, Protestant, and other included to the model without Catholic, Protestant, and other included. So we really have here a situation of two nested models, because the first model constrains the coefficient for Catholic and the coefficient for Protestant and the coefficient for other, so the coefficients B4, B5, and B6, to take the value 0, because only if they take the value 0, we can drop them from the equation. So these are really classical nested models that we have here. So I did this. I asked SPSS to estimate these two models as nested models, and I put an example syntax on Brightspace that shows you how to do that. And then I'm getting a lot of output, because with logistic regression analysis, SPSS has the tendency to provide you really with lots of different outputs, which are basically systematized by the different models that you're estimating. So for linear regression models, SPSS condenses this quite nicely, but for linear models, it condenses it quite nicely. For logistic model, it splits it all out. So you get each block refers to a model that you have estimated. So in this case, block 1 refers to the first model that I have estimated. So this is the model with differences in age, gender, and income only included. And then the table that you want to look out for is the so-called omnibus test of model coefficients table. So this one here, where we see step 1, step block model chi-square degrees of freedom and 6. So in other words, we have a p-value, chi-square test statistic, and a degrees of freedom indicator. So what does this tell us? Well, it does what in linear regression model the ANOVA table tells us. So it tells us how much of improvement in the goodness of fit is the first model that we estimated, so the simpler of the two models. How much of improvement in goodness of fit is that relative to the overall most simple model that we could ever estimate. So that's a model with no independent variables, so just a model for the B0 coefficient. Yeah, remember in the linear regression model, the ANOVA told us about the improvement of goodness of fit of any model that we estimated relative to just using the constant as a prediction, which came down to just using the mean as the predicted value for our dependent variable. In a logistic regression model, it's exactly the same logic. The most simple model that we can estimate is the one with no independent variable. So we just get a B0 coefficient, which is then just, well, the log odds of voting. So the natural logarithm of the odds of voting in our sample. Yeah, so with this omnibus test of model coefficients, we are testing the improvement of goodness of fit from having no independent variables to predict the log odds of voting, to having differences in gender, age, and income predict differences in the log odds of voting. And you can see from the degrees of freedom that are reported here, this is listed as 3. That makes sense, because the difference between this model and this model is that for this model, we are constricting or constraining B1, B2, and B3 to take the value 0. In other words, we are putting 3 constraints on our model to get to this most simple model with no independent variables. So what we get here is a chi-square test statistic, which is in this case 34.768. So that's the difference in deviance between this model and this model, which SPSS automatically compares for us to a chi-square distribution with the correct degrees of freedom, because SPSS correctly saw that there's 3 constraints that we are putting on the model to get to the most simple model, and it gives us a p-value for that. So in other words, what is the probability of finding this difference in deviance or a larger difference in deviance, so this chi-square test statistic or a larger chi-square test statistic, under the null hypothesis assumption that there is no difference of goodness in fit between the model where we're just using the log odds of voting to predict voting compared to the using a model where we're using differences in gender, age, and income to predict the log odds of voting in the population. And again, in this case, we see a pretty low p-value, meaning that we would be quite confident to reject that null hypothesis in favor of the alternative hypothesis that differences in gender, age, and income at least lead to some improvement in predicting the log odds of voting in the population. So there is a significant increase in the goodness of fit by including these three independent variables. Now, I asked also, of course, for the second model where I'm also including the dummy variables for Catholic, Protestant, and other. So SPSS will report then those as block 2 because it's the second model that I ask for. And again, I will get this omnibus test of model coefficients table. And now you see that it looks a bit more interesting because now we have two different chi-square values in there, 6.428 and 41.188, two different degrees of freedom, 3 and 6, and also two different probability values, p-values, 0.093 and 0.000, rounded to 0.000. So quite small. So what does this model tell us? Well, this model, this table is about the second model that we estimated in this case, which was the model where we included gender, age, income, and the dummy variables for religious domination as x variables in the model. So at the bottom of this omnibus table, it still gives us a chi-square test statistic that is about this entire model compared to the so-called null model, where we are just using the log odds of voting to predict whether or not people voted, right? So in that case, what is reported at the bottom here is the deviance test that tests the improvement in goodness of fit from just using B0 as a prediction of voting relative to using the entire model with differences in age, gender, income, and religious denomination to predict differences in voting. Yeah, so in this case, you see correctly that the difference in deviance is calculated to be 41.188. So that's the difference in the deviance between these two models. And we see that the degrees of freedom are correctly reported as 6. That makes sense because B1 and B2 and B3 and B4 and B5 and B6, so 6 different coefficients, were constrained to take the value 0 to get to this most simple formula, this most simple model. We are just using the log odds of voting that we observe in our sample as a prediction for whether or not people voted. So in this case, you see quite a low p-value. In other words, we would be quite willing to reject the null hypothesis that take into account differences in gender, age, income, and religious domination at no additional information on differences in voting in the population. Yeah, so we have a significant improvement in the goodness of fit, going from the most complicated model that we're estimating relative to the most simple model that we can even think about. The part on top of that is quite interesting now, because here now we see that what SPSS has done for us, it tested the improvement in the goodness of fit from our more simple model where we had gender, age, and income as x variables to the more complicated second model that we estimated, where we have not just gender, age, and income, but also the dummy variables for religious denomination. So in this case, you see that we get a different chi-square value because it's about a different comparison. It's about a difference in deviance from this model with gender, age, and income included to this model with gender, age, income, and religious denomination included. So you get a different difference in deviance value. So you get a different chi-square test statistic, and you get a different degrees of freedom, 3 in this case, because in this case we are comparing the model with B4, B5, and B6 estimated to a model where we are constraining B4, B5, and B6 to take the value 0. So we are taking out the dummy variables for Protestant, Catholic, and other religious denomination. So in this case, you see, yes, this gives us a different probability value, in this case 0.093. So in other words, in this case, we would say if we are very, very strict with an alpha of 0.05, we would not be able to reject the null hypothesis that the model with differences in religious denomination is significantly better in predicting voting in the population than the model where we are only using differences in gender, age, and income. So we would not be able to reject that null hypothesis if we would be very strictly working with an alpha of 0.05. Yeah, so in other words, a multi-parameter test of the null hypothesis that the free dummy variables we use for religious denomination are 0 in the population shows that we can't reject that null hypothesis. Okay, so that's all of that is quite analogous to how it works with f-tests. In the linear regression model, it's just that the tables get different names and presented in a slightly different way, but the underlying logic is exactly the same. So once you have seen that, hopefully it's not going to be terribly difficult to work with nested models and compare the goodness of fit of different nested models. Now to close off, let's talk about assumptions, because as with any model to analyze our data, whether it's a statistical model or a non-statistical model, we are going to make certain assumptions. And those assumptions may or may not be true. And if the assumptions are not true, then that can lead to bias in our results. And it's no different for logistic regression models. So as always, a violation of the model assumptions can lead to biased estimates. So what are the assumptions for a logistic regression models? For a logistic regression model? Well, some of them are quite familiar. Some of them are different than in the linear regression model. So for one thing, what is familiar is additivity and linearity. And we are also assuming additivity and linearity in a logistic regression model. But meaning additivity and linearity is assumed for the effect of our x variables on the log odds of the event that we're interested in analyzing. So not to the probability that the event happens, not to the odds that the event happens, no, to the log odds that the event happens. Yeah. In other words, we are estimating a linear additive model for the predicted log odds. That means that it has to make sense to assume that there is a linear effect of our x variables on the predicted log odds. So for instance, where might this not be the case? Well, for instance, if the true effect is a curvilinear effect. So let's say we want to estimate the effect of H on voting. We estimate a logistic regression model. Well, if the true H effect is a curvilinear effect, and we are just using a linear effect, so just the original H variable as an X variable, then we would be violating this assumption of linearity. Yeah, so that basically is the same as in a linear regression model. The only thing you need to remember that is that we assume additivity and linearity of the effect of our x's on the log odds of the event that we are analyzing on the event that represents our dependent variable. What is also the same is that we assume that the errors are independent, meaning that we cannot systematically predict the errors of cases knowing the errors of other cases. And that is basically exactly the same as in a linear regression model. So when is this problematic? For instance, if you have the same units of analysis that you have observed multiple times, which means that your dependent variable, even if that is an event, there's probably going to be some similarity within the same units of analysis that you've observed multiple times on experiencing that event, which means that the errors won't be independent. You will get some degree of serial correlation or autocorrelation. Or if you have, for instance, a multi-stage sample, so for instance, using the European Social Survey data on all the different countries, where basically what happened is first the people from the ESS selected different countries, and within those countries they selected individual people. So in that case, belonging to the different countries will often lead to some degree of similarity on the dependent variable. Also, if that's just an event that could happen or could not have happened. Think about the systematic differences in voting between countries or taking part in strikes between countries. So that means our dependent variable can be similar within some kind of higher level unit that we observe. Then we get intra-class correlation that is going to lead to a violation of the assumption of independent errors. So that's the same as in the linear regression model. There's no real change there. What is a bit different, of course, that we are no longer assuming homoscedastically and normally distributed errors. No, we're actually assuming we make an assumption about what the distribution of errors is. That is the distribution of error is consistent with the binomial distribution. But that means that this actually has to be true. So this variance of error needs to be actually consistent with the binomial distribution. And if that's not the case, then that can lead to bias in certain situations, which I'll talk a bit more about in about 2 minutes, because that one that works a bit different than in the linear regression model. But first, some other general stuff that's really the same. Outliers and multicollinearity is the same as in the linear model. If you have outliers, that can lead or multiple collinearity, that can lead to bias or untrustworthy estimates in the same way that this happens in the linear regression model. So nothing really here new. That is new. Sample size also to some extent similar, in the sense that more observations are always going to be better, assuming that they are sampled correctly. In the sense that then we get more reliable estimates. The one thing you need to worry about or need to be aware of if you have a logistic regression analysis is that because you have a dependent variable where something either happens or it doesn't happen, you need to consider both of those categories when you think about your sample size. For instance, if your dependent variable is whether or not people voted in an election, then don't just look at the overall number of people that you observed, but also look how many people actually did vote and how many people did not vote. And be aware that with logistic regression, you should really take into account both of these categories. Because, let's say, for instance, you have a situation where you have 1,000 observations for voting, and 999 of those people actually voted and only 1 people did not vote. Then from a perspective of a logistic regression model, you really don't have 1,000 observations. It's closer to having 1 observations or 2 observations. So you really need to have a healthy number of observations in each category of your dependent variable. So my rule of thumb would be, and again, this is really a rule of thumb, so it's no law. This is no, if this is true, then you're doing great, and if it's not true, you're doing terrible, but it's kind of a rule of thumb you can go by, is look at the smallest category of your dependent variable, so that one that has the smallest number of observations. And then in that category, try to have at least 10 observations per independent variable in your model. That is a rule of thumb that you can follow. But again, it's just a rule of thumb, so sometimes you need more than that, more than those that number of observations to get reliable estimates. And sometimes even if you have a smaller amount of observations per X variable in the smallest category of your dependent variable, you might still have decently reliable estimates. So this is just a general rough rule of thumb. So let's talk about this third assumption in logistic regression a bit further. This variance of error needs to be consistent with the binomial distribution. Why is that? What does it mean? We already saw that this is what we do assume, that we assume that our error is the error that's implied by the binomial distribution, because we need to make that assumption to be even able to find our regression coefficients. So, in other words, because we cannot separately estimate probabilities and the error corresponding to those probabilities, because we only observe zeros and ones, we have to make an assumption about the distribution of the error, as we have already seen in this lecture. Now, the thing is, that means that the unexplained variance that we have in our model is going to be assumed to take a fixed value. This might seem a bit weird, but this is really what we're doing. If you make an assumption about our error term, that means that we are making an assumption about, okay, how is the unexplained variance, what does that look like? And for a logistic regression model, we assume a binomial variance, and that means that actually we can say, well, there is a number that represents this unexplained variance that is always going to be the same number. So there's a couple of different ways of thinking about that. One is you can think about the logistic regression model as a model for some kind of latent overall propensity for some event to happen. And if we would express the model in that way, there is actually a simple formula that describes the exact value of the unexplained variance, pi squared divided by 3, which works out to around about 3.29. Now, you don't need to know how that works. You don't need to know why that is. The only reason I'm showing it to you is so that you know that there is one single number in that logistic regression model which we assume to describe the unexplained variance. And it's always the same. It doesn't matter what model you're estimating, with which cases and which x variables and which transformations. All of that doesn't matter. We always assume that the unexplained variance in our model takes a fixed value that in some formulations of the model can be worked out to this value of 3.29. So it is a fixed value. And what happens then is basically that because we need to make the assumption about this error, we're assuming it to take this value of 3.29. So when we're estimating the model, basically our logit coefficients are standardized in such a way that our residual variance always takes this value. Yeah, so assuming a binomial distribution of the error basically means that the model that we're estimating, so the coefficients that you get for the logit model, are standardized in such a way that residual variance actually is this value. Yeah, because otherwise there is no way to find values for these regression coefficients. And most of the time that's completely fine. You can think of that as being a bit like standardizing in the linear regression model where we used z-scores to standardize. Was that terrible? No, not really. It's just expressing your coefficients on different scales, on different scales, so that it makes sense for what you're trying to do. And it's the same for the logistic regression model. Most of the time, that's really not problematic. We're just changing the scale of our b variable in such a way that it makes sense for the model that we want to say something about. But there are specific situations in which this assumption can actually be problematic. And there's roughly two situations in which this is the case. If we want to compare effects across different groups or different models, or if our logit model is estimated with aggregate events. Yeah, so far we talked about the binary logit model, and binary implies that for each individual case we observe whether or not that case experienced the event or did not experience the event. But logit models can also be used for analyzing the aggregate number of events. So for instance, think about situations where you have counts or proportions that you are able to analyze, but not individual cases. So for instance, let's say you want to explain differences in the probability of voting across different countries, and you didn't actually observe individuals within those countries, but you did observe the overall percentage of people that voted, or the number of people that voted, and how many people there are in such countries. Yeah, so then we have the aggregate number of events. So then we don't know for individuals whether or not they voted, but we do know on aggregate what the proportion of voting looks like in these different countries. And you might want to use that as your dependent variable in a regression model. And then for instance, use stuff like types of voting party systems or voting systems as independent variables. Well, in that case, you might still want to estimate a logit model because it is based on aggregated events. And then you can still basically say, well, we still have the same issues with the linear regression model as we have if we have binary data. So the logit model might still be a good solution to that. And as a matter of fact, it's quite common to use a logit model for these aggregate events because of these reasons. And also there, this assumption sometimes can be a bit problematic. So let's first consider the first situation. If we want to compare effects across different groups or different models. So exactly what is the issue here? Well, our coefficients in a logit model are in a sense standardized. So we change the scale in such a way that the residual variance in our model, so the unexplained part of the variance, is that one value that we assume it to be, again, which works out in certain formulation of the model to around about 3.29. So, but the important part is we are rescaling our regression coefficients so that residual unexplained variance exactly takes this one value, the only value that it can take. And that means that the value of our estimated regression coefficient now depends on two different things. What the actual effect is of our x variable, so the true effect of our x variable on our dependent variable, but also how much rescaling was needed to make sure that the unexplained variance gets to this assumed value. Yeah, so our regression coefficients basically now capture two different things: the true effect, but also how much rescaling was needed to make sure that the unexplained variance is the same as it takes the value that we assume it to have. And of course, the true amount of residual variance, so how good our model is at predicting the outcome, can be different across different types of different groups in our data set. Yeah, so think about, for instance, if we want to say something about the effect of gender on voting, then our model might be better at predicting voting for men than for women. So the true amount of residual variation might be different across different groups. And it will, by definition, always be different for different models. Yeah, so if a model with more X variables, then you are explaining, by definition, more variation in your dependent variable. So models with different sets of X variables included will have different true amounts of residual variance, which means that the different amount of true residual variance means that there is going to be a difference in how much we need to rescale our regression coefficients so that the residual unexplained variance in our model is taking that assumed value. So different amount of true residual variances lead to different scales on which our B coefficients are expressed. Which means that in a logistic regression model, this is really different from a linear regression model, comparing regression coefficients across models estimated for different groups. Yeah, so for instance, estimating a separate model for men and for women, or for estimating separate regression models for different countries, or across different models for the same set of observations. Yeah, so models with different sets of X variables included. We cannot just compare the coefficients in that case and assume that any difference that we see is only due to the true effects of our X variables, because the value of our coefficient doesn't just depend on the true effect, it also depends on the amount of true residual variation, because that amount of true residual variation has an impact on how much rescaling we need to do to make sure that the residual variation that we get takes the assumed value. So in other words, comparing coefficients, regression coefficients, isn't the same thing in logistic regression model as comparing the true effects, because they depend on two different things, the true effects, but also basically the amount of true residual variance that we have. When would we do that? Well, for instance, if we have interaction effects, because if you think about that, what is an interaction effect? If you think about it, it is comparing effects across different sets of observation, different groups. Yeah, so for instance, if you have an interaction effect between income and let's say religious denomination, and let's assume we have measured religious denomination in these different groups, Catholic, Protestants, and others, and non-religious, then if you have an interaction effect between income and religious denomination, what we're really doing is we're saying, well, how does the income effect differ between the non-religious, the Catholics, the Protestants, and the others? So interaction effects really are situations where you want to compare the effect across different groups, across different categories in your data set. So that's an issue. The other issue is if you do mediation analysis, because how did we do mediation analysis? We compared different models. We compared a model where we did include the mediator variable to a model where we did not include the mediator variable, and then we looked how this did the effect of our X variable change. Well, in a logistic regression model, this is problematic because in both of these situations, so for interaction effects and mediation effects, the change in the regression coefficient, either as it is implied by the interaction term or as you observe it for estimating these different models, these three different models you do for the mediation analysis, isn't just reflecting the true changes in effect, but it's also reflecting the differences in the true residual variance. So the amount of rescaling that is needed to get to be able to estimate your regression coefficients. So that means that you can have quite a bit of bias going on if you do interaction effects or mediation effects in logistic regression with logistic regression models. So that's not so good. What is good news is that there are actually a couple of very good solutions available to this problem where we can use logistic regression analysis and just solve these problems in a very nice way so that we can still do reliable interaction and mediation effects. But of course, as always with me, if I give you good news, I'm also going to give you bad news. And the bad news in this case is that most of these solutions aren't well integrated into SPSS yet. So either it's very, very difficult to nigh on impossible to actually use SPSS to implement these solutions. But there is one solution that you can do quite easily with SPSS. It's a bit rough, but it can work quite well. And that rough solution is as follows. Well, if you think about what is the underlying problem here, the problem is that the error term in a logistic regression model, the variation of that, the distribution of that error term is an assumed variation, because we can't actually independently estimate that, which we can do in the linear model. So linear or less estimated model don't have that problem, because the unexplained variance is not something we assume, but something we can simply observe from our data. We fit a linear regression line, and then we can just see, well, okay, how good does that regression line fit with the individual observations? And then we can calculate an R-square, so that's the explained variance, and we can calculate 1 minus the R-square, the unexplained variance. So in linear regression models, we don't have the problem that we have to make an assumption about the distribution of our error term, the assumption about the variation of our error term. We can just see, well, what does it look like in the sample that we observed. So linear regression models don't have this problem. And in certain situations, linear regression models can be applied to a dummy-coded dependent variable. They are then referred to as linear probability models. So if you just have a dependent variable where you say, I'm giving the cases that didn't experience the event the value 0 and the cases that did experience the event the value 1, then I can just estimate a linear model using OLS. That's then referred to as a linear probability model, but it's really just a linear OLS model for a dummy-coded dependent variable. And then we have already see that these estimates can be biased. And that is true. But even though they may be biased under certain conditions, they can actually be consistent, meaning that the further we increase our sample size, the closer the regression coefficients we get from such a linear probability model are going to be to the true effects. So this is what this here says, is that as n goes to infinity, so as our sample size becomes larger and larger and larger, our regression coefficients in this model are going to get closer and closer to the true effects. Yeah, so this is, in statistical terms, we call that consistent, meaning that it's not necessarily unbiased. So on average, the estimates may be wrong, but the further we increase the sample size, so the larger our sample is, the closer on average we get to the true effects. And then hopefully at some point our sample is so large that there is no substantial difference anymore between what we get from our models and what the true effects are. And if you consider the logistic regression model, well, it describes this S-curved effect of our X variable on the probability of something happening. And if you look at this S-curve, you might notice that a linear prediction for the predicted probability is very, very bad. Right, because it leads to predicted values outside of outside of 1 and below 0. We don't want that. So the logistic transformation makes sure that the predicted probabilities can't go below 0 and can't go over 1. So we get this S-curve. But if we look at what that S-curve actually looks like, you see that if you would consider, let's say, the range from around about here to around about here, so right around here, so positive predicted values that are reasonably close to 0.5 and not close to 0, and predicted values that are reasonably close to 0.5 and not close to 1. So all those predicted values basically where we are not close to 0 and not close to 1, so those in between. If we look at the relationship here, it's not a strictly linear line, but the linear line would do a pretty good job of describing this relationship. Yeah, so if you just look at this part of the S-curve here, a linear line is almost as good as as this logistic regression line for predicted probabilities. Yeah, it's only really, the problem only really starts when we get very, very close to 0 and very, very close to 1. So, and this is the situation where we could say, well, a linear probability model might actually not be terrible. If we would say, well, the predicted values that we find from such a linear regression model are mostly well within this range over here, where really the change in predicted probability from a logistic regression model would also be more or less just a straight line. So what does all of that mean? It means that the linear probability model might still be pretty reliable in giving you the right estimates for your coefficients, assuming that you have a pretty large sample. Yeah, so relying on the idea that it is consistent, and if your predicted probabilities are mostly well within 0 and 1. So if the predicted probabilities from your linear probability model are if you don't have a bunch of predict probabilities for cases that are negative or larger than 1, if most of them are really within 0.0 and 1 and preferably right around the 0.5 value, yeah, so let's say most of your predicted probabilities in your sample are somewhere between 0.2 and 0.8, yeah, then okay, probably your linear probability model is going to be pretty reliable actually, and you could actually just use that to estimate the effect of your X variable on the predicted probability of something happening. Standard errors will still be problematic because, yeah, those are specifically relying on this assumption of homoscedastic and normally distributed errors, which obviously we don't have in such a case. But we already saw that there are solutions to that. For instance, we can use the bootstrapping procedure to, instead of relying on the estimated standard coefficients to make inferences about the population, we can bootstrap our distribution of regression coefficients by repeatedly sampling from the observed data and in such a way trying to reconstruct the sampling distribution of our regression coefficients. Yeah, we already saw that we can do that. There was already an example as syntax that you hopefully have taken a look at where it is shown how to do that. So we could just use bootstrapping to make sure that we have usable standard errors to test null hypothesis, for instance. Yeah, so in other words, under certain conditions, so if you have a large n and if the predicted probabilities are well within 0.0 and 1, then the linear probability model isn't necessarily terrible for a dichotomous binary dependent outcome. So I would always recommend, if you have to use SPSS and you want to do interactional mediation analysis, or just in general compare coefficients across different groups or different models, then besides your logit estimates, so your logistic regression analysis, redo your analysis also with a linear probability model, and then especially if you have a large data set and you see that the predicted probabilities aren't too far outside the range of, so well within the range of 0 and 1, then just check whether there's any substantial differences between the linear probability model and the logistic model to assess whether the effects that you find are robust to this issue. Yeah, and of course, if there are, report this to your reader and report the results of both of those models. And I would say in those situations, if you have a large data set and if your predicted probabilities are well within 0 and 1, so no super weird predicted values, then the linear model is probably going to be a better estimate than a logistic regression model for your interaction and mediation effects. Yeah, so this is a way of solving that. Now, one more thing that we need to talk about when we talk about the distribution of errors that we haven't yet talked about, if the logit model is estimated with aggregated events. It's not something that we really do in this course. We just assumed a binary dependent variable where something happens or it doesn't happen, and we can observe that for all individual cases. But in some some situations, you might just have the aggregate number of events, so the proportions per countries or municipalities or something like that. And then you might still want to estimate a logit model because, you have basically the same issues as you would have with binary data with as the assumption of linearity and additivity, homoscedasticity, and normally distributed errors. So that's quite common. There is one issue then again here. The true variation that you might find in your dependent variable might then be more than what would be assumed by the binomial variance that we are assuming. So sometimes you might have more variation going on in those aggregate proportions or counts than you would assume based on a logistic model. So when that is the case, that is referred to as over-dispersion. So dispersion is just a different word for spread or variation, and over means, over more. So in other words, sometimes you might have more variation going on than you would assume based on the model. And sometimes the reverse might happen, that you have actually less variation going on in those proportions or counts across your cases than you would assume based on a logit model. Over-dispersion is more common. Under-dispersion, so if you have less variation than you would assume, that's not very common to find that. So what is the issue then? Well, over-dispersion usually is a result of violating the assumptions of additivity and linearity. or the independence of your error. It might be also the case that your errors aren't independent, or it could point out that you just have a badly specified model. So maybe there's lots of variables that are missing from your model that should be included in the model, or there's lots of interactions and nonlinear effects that you haven't included in your model but that really should be in there. So any of those issues might cause over-dispersion, basically meaning that you have more variation going on than the logistic model actually assumes. As always, there are statistical solutions to that. So then there are other models that you could take a look at. For instance, the so-called negative binomial model is a bit like a logistic regression model, but in that case, there is an added estimation of the variance that you can use to allow for there to be more or less variation than you would strictly assume based on a logit model. So those are potential alternatives that are available to you. The one thing that you should note, because all of this is like, if you ever go on in real life on your further studies with doing those kinds of logit models, it's important that you've heard about that, but it's not terrible if you don't know all of this already for this course. I just thought it would be important to already tell you. The one thing that you should be aware of, because you might see in some textbooks that these issues of over and under dispersions are talked about as potential problems, or maybe your teacher in one of the next courses will talk about that there may be problems, or if you go on to do research, your reviewers might say, well, this might be a problem. You should be aware of one thing. This issue of over or under dispersion for logistic regression models, that's only a problem if you're talking about aggregate events. If you have binary data, this is not an issue. This is only if we have aggregate number of events that we are analyzing. So we don't know for the individual cases whether it happened or it didn't happen, the event that we're interested in, but only at the aggregate. Then over dispersion or under dispersion might be issues if you know for each individual case whether or not the event happened. So if you really have binary data, then over dispersion isn't an issue that can actually cause any problems for your analysis. So that's about that. There is a couple of technical issues you can run into with logistic regression models that are always a risk. So it's important to be aware of those. So what is the problem? Sometimes there are situations here where you might notice that SPSS isn't able to estimate the model for you, or if it does estimate the model for you, you get all kinds of error messages, or coefficients aren't being represented in the tables. And there's basically two things that can lead to this situation. One is the situations referred to as incomplete information. And the idea is that if you want to be able to have a maximum likelihood estimate for your coefficients, then all the combination of x values, so for all the different independent variables that you have in your model, all potential combinations of values on those x variables should to some extent be present in your data. And the less this is the case, the more of a problem you have with not having sufficient information to get a maximum likelihood estimate. So for instance, think of a very simple example that maybe I've measured two variables among a group of students, whether or not they made all the assignment and whether or not they showed up to the Zoom meetings. And I'm using both of those as dummy variables to predict whether or not students passed the grade. So I'm using a logistic regression model with a dummy for did all the assignments, and a dummy variable for showed up to all the Zoom meetings. And I'm trying to use those as X variables to predict whether or not people passed the course. So what would be incomplete information? Well, let's assume that we have all the students that made all the assignments are also all the students that showed up to all the Zoom meetings. Then there is no combination of students where we have students that did make all the assignments but did not show up to all the Zoom meetings, or vice versa, that did show up to all the Zoom meetings but did not make all of the assignments. So in that situation, we have an incomplete information. There are combinations of X values in our data that are in theory possible, but that are in practice not actually observed in our data set, and that can lead to problems with estimating your logistic regression models. Now, this is a bit of a matter of degree. For instance, if you think of a variable like age, yeah, of course, you won't have for each individual observation of age, because it's a pretty broad scale, every potential combination of all the other X variables present in a data set, unless you have a really huge data set. But yeah, the lower number of categories are, the worse this problem becomes, basically. Yeah, so that might be an issue. Well, if that is an issue, I would say always check the cross tabulations of all your categorical variables in particular. So if you have lots of variables like gender measured in categories, socioeconomic status measured in categories, religious discrimination measured in categories, then do cross tables of all your categorical X variables and see if there are any kind of combinations that aren't present in the data. And if you do find those situations where you see certain categories just don't exist in my data set, so you have no observations in that combination of categories, then you have to somehow simplify your categorical values, so merge categories. So for instance, if you're using 3 different categories for religious denomination and you find that then there's lots of religious denominations where you have no observations in combination with other X variables, well, then just reduce the number of categories, merge categories. So for instance, just make one variable for religious versus non-religious. That will then help to solve these problems. So usually a problem of incomplete information is just that you're trying to estimate too many parameters from too few observations on your X variables. So the solution is always, you have to simplify your model in some ways. Most often it is the case if you have categorical access using lots and lots of dummy variables, then probably you're trying to estimate too many dummy variables, and for some of the dummies there isn't just enough information present in your data to estimate them. Yeah, so that's one. The other issue that you might run into, and it's a bit related to that, is the issue of complete separation. Complete separation meaning that it might be the case that one of your X variables or a combination of your X variable perfectly predicts the outcome. So perfectly predicts the probability of experiencing the event, of not experiencing the event. So coming back to this example of trying to predict whether or not people pass the course based on whether they took part in all of the meetings and made all of the Zoom meetings and made all the assignments. Well, it could in theory be the case that people that made all the assignments always also pass the exam. As a matter of fact, that's quite likely. So in that case, the variable making the assignments, making all the assignments, is a perfect predictor of whether or not people pass the exam. So it perfectly predicts the probability of passing the exam. So that is an issue. So if you have an X variable or a combination of values on the X variable for which we see that the outcome is always the same, it's either 0 for all the cases or 1 for all the cases, then we get this issue of complete separation. And why is this a problem? Well, we're using this maximum likelihood estimation procedure that tries to maximize the value of the likelihood. But if you have this situation where one of your X variable, of a combination of your X variables, perfectly predicts the outcome, then basically that value for the likelihood goes to infinity, and you can't mathematically work with that value anymore. So then you're not able to actually estimate the models. So this might seem a bit weird. That can our models actually be too good in explaining the outcome? And yes, they can be. If our model is able to perfectly predict the outcome, then we aren't able to find the solution to our model anymore. So we are no longer able to estimate the coefficients for that model in a logistic regression model. Now there are some very fancy technical solutions to this problem also, where we're still trying to have estimation procedures that do and that are able to find the regression coefficients. But usually the problem is if you have this situation, it's just that you're asking too much from your data so that you're trying to estimate too many coefficients with too few actual observations, because that is when it's quite likely that an X variable or a combination of X variable is able to perfectly predict the outcome in your sample data set. So usually the real issue is your model is just too complicated for the amount of data that you have. So simplify the model in some way. Try to estimate fewer X variables at the same time. If you have many categorical variables with many dummies that you include, try to merge categories. So make larger categories so that you have more variation going on, and then there's less likely to be a problem of complete separation in your logistic regression estimates. All right, that was it for me. I would say, well, for one thing, of course, good luck on the exam. I will post a couple of pointers for the exam on Brightspace this week. Yes, enjoy, and well, don't subscribe, don't hit any kind of notification button, and the only bell that you need to worry about is that implied by the normal distribution. I'll be seeing you. Good luck and ciao, bye bye.